Welcome everybody to the afternoon session of the first day of String Math 2021. Before I introduce the speakers, let me just remind people that if you have questions, you have several options. One is to post it to everybody on the chat, and hopefully there will be a vigorous discussion. People often answer other people's questions. If you want to ask a question to the speaker, just raise your hand and I will, when we get to reasonable stopping places, I will ask the speaker to address your questions. And finally, there will, at the end of the talk, of each talk, there will be a question and answer session, and you can raise your hand then or just speak directly. So it's a great pleasure to introduce Tom Bridgeland from Sheffield, and he will talk, as you see, about geometry from Donaldson-Thomas invariants.
Okay, thank you very much, Ron, and thank you to the organisers for inviting me to speak at this excellent event. I love coming to String Math. It's exactly the sort of conference I find really exciting. So I'm talking, I'm sort of going to try and give a progress report on a kind of a line of research which is a little bit experimental, it has to be said. So anyway, I will try and show you some of the results that have been obtained so far and give some pointers for future research. So, so mathematically, you could say that what we're trying to do is somehow encode Donaldson-Thomas invariants in some geometry. Right, so naively you could think of the analogy whereby it's a very kind of well-known story, important part of mirror symmetry, that genus 0 Gromov-Witten invariants can be encoded in a Frobenius structure, and so that's one naive motivation for why you might want to ask: are there any geometric structures around which somehow encode Donaldson-Thomas invariants? I mean, for me, really, the motivation is that there's this very exciting bridge between maths and physics, which sort of focused around DT invariants and wall crossing. I mean, I think that's a sort of a little piece of the subject that we understand quite well from both maths and physics points of view, and we understand each other. So it's natural to somehow want to build out from that mutual understanding. And the key point for me there is that mathematically, we have a very general theory there. Really, it applies to any triangulated category with this CY3 property. And that's a powerful thing. Okay, so I should say, really just to orient people who already know about these things, that the main technical part of the subject is a class of Riemann-Hilbert problems, which at least are closely related to some problems studied by Gatto, Moore, and Neitzke more than 10 years ago now. And just to say that certainly what we are doing is very closely related to what they were doing, but strictly speaking, it's different. And I think the right physics thing to say here is that we're considering the conformal limit. What it comes down to is that we're considering a different boundary condition at infinity for our Riemann-Hilbert problems. But we'll come on to that in a minute. And the other thing it's worth comparing what I'm doing here with is, there's a current line of research coming from physics. For example, the work of Mourinho, studying resurgence properties in quantum field theory. So, for example, work of Xi, Gu, and Mourinho, they studied the topological string partition function of a toric Calabi-Yau threefold. And that is some formal series in the string coupling lambda. So in other words, it's the Gromov-Witten generating function, and lambda is the genus parameter. And that formal series is not convergent, but you can try to Borel sum it. And if you do, you get various different answers depending on which direction you Borel sum. And you can compare those answers and extract kind of integer invariants, BPS invariants. Well, that's what you would expect somehow. So they're somehow starting with the partition function, or rather the free energy, Borel summing, comparing different Borel sums and extracting BPS data. What we're trying to do somehow is the opposite direction. You start with the BPS data, and as we'll see in some examples, you can get at the partition function. But of course, what we're doing, I mean, if you know, I mean, you can imagine this is somehow the wrong way around. It's better to start with the, well, somehow, what we're doing is a kind of inverse problem. We're starting with the Stokes data and trying to reconstruct the differential equation. But anyway, the reason, you know, at least we're trying to do it this way around is because we're starting with data that's mathematically very well defined, the DT invariants. Okay. And this, I should say, this whole subject is kind of rather abstract and speculative in general, but there is some concrete class of examples, which I think in physics would be called theories of class S, with, you know, there is an ADE parameter in there, and I'm taking A1. So this is some kind of rich class of examples where everything relates to things like quadratic differentials on Riemann surfaces, and, well, yeah, so you can relate things to concrete mathematical objects. Okay, so generally just do please ask questions, but I will continue. Oh, and I should just say that if you're interested in at least reading my point of view on this subject, these are the two references that you could start by looking at. Okay, so what data do we start with in this topic? So from the mathematical point of view, which is really all I'm qualified to speak on, I take a triangulated category over the complex numbers, and I insist that it has this CY3 property. So the basic examples you would want to think about are the derived category of coherent sheaves on a Calabi-Yau threefold, or the Fukaya category of a Calabi-Yau threefold. But more likely, in, you know, for what I'm saying, you would want to think about some much simpler examples defined algebraically by quivers. Okay, and then the other piece of data I need is some stability condition on this, which is some algebraically, you know, there is some algebraic definition of what a stability condition on a triangulated category is. And I'm not going to go into that just now, but mathematically, that's the starting point. So physically, as I say, I'm not really qualified to say, but and I'm very happy for people to butt in and correct me here. But you know, one of the things you could be studying is a theory of class S at this time. I mean, more generally, some class of supersymmetric quantum field theories with n equals 2 supersymmetry. And then, you know, what does fixing this stability condition correspond to? I mean, again, I don't really know. For example, in this class of examples, theories of class S, this data corresponds to fixing a point of the Coulomb branch. Okay. And then once we've fixed, you know, once we've done this, what data do we get out? Really, I mean, I tend to call this a BPS structure, but I don't expect you to take me seriously when I do that. What it is there's a lattice, gamma, some free abelian group of finite rank, with some skew-symmetric form on it, taking values in the integers. There's two other pieces of data, namely there's a central charge, which is a map from this lattice into C, and the BPS invariants, which are kind of the interesting bit of the data, really. So for each class in this lattice, each charge, I have a BPS invariant, which is somehow counting, well, counting semi-stable objects of class gamma in some sense. So how would this look if we were just heuristically to take D to be the Fukaya category of some compact Calabi-Yau threefold? Okay, so this charge lattice would be the third homology, is how I would guess. I mean, I could be saying something that are mildly incorrect here. I mean, whenever I talk about the Fukaya category, I'm talking about it in a rather heuristic way. But let's just try and communicate something here. So gamma, I would take to be H lower 3, the third homology group of my threefold, because every Lagrangian submanifold has some charge, has some fundamental class in there. This skew form would just be the intersection form. The central charge would be integrate against a holomorphic three form. Okay, so so I should say that fixing this stability condition, you could think about, well, if I choose a complex structure, once I've chosen a complex structure on my Calabi-Yau threefold, I expect to have a stability condition, and this central charge is integrating the holomorphic three form against the Lagrangian, so or against the class in H3. And then the BPS invariants are somehow counting special Lagrangians of a given homology class. That's somehow the idea. Okay, but I hope that physicists in the audience will somehow know what I should have written here and understand that once this data is fixed, they indeed have a charge lattice with a form and a central charge and these invariants. I should say that from a mathematical point of view, from a mathematical point of view, this is some quotient of the Grothendieck group of the category. This is something called the Euler form. This central charge is part of the data of a stability condition. And these BPS invariants are the DT invariants. And then just some more data I need to extract from here. Well, just simple. I need to introduce some torus. So it's the torus whose character lattice is gamma. So it's a copy of C star to the n, and it's got these characters indexed by the elements of the lattice. The skew symmetric form I have means that there is some invariant Poisson structure on this torus, which on characters looks like this. And then I've squirreled this away at the bottom of the slide, but it's very important. There are certain birational maps from this torus to itself, given by this formula on characters. Okay, so there's one of these birational maps for each charge gamma, alpha. So for each element of this lattice, and then it's given by this formula. So if you think about the basic characters xi, the coordinates on C star to the n, in other words, it means it goes xi goes to xi times 1 plus some monomial to some power. Okay, some fairly basic birational maps. And then I told you all this because I want to now tell you what the wall crossing formula is, how these DT invariants or BPS invariants change as I change my stability condition sigma. And I'm just going to go through this briefly. So first,
Tom, Tom, if I may ask a question, are you going to use more general birational transformations like 1 minus x beta to the -2?
I'm certainly going to raise this to the power of something, so that would bring me a -2 up here. There is a whole issue of signs here, which I'm basically ignoring. So, I mean, think about this as 1 plus or minus. I mean, I take it this question was from Greg. Yeah, I'm sorry if this isn't, I should have said this. In theory, here there should be a plus or minus. Sometimes you should take plus and sometimes you should take minus. And indeed, you want to raise this exponents to powers, which will be the DT invariants. So indeed, this is what I want to do here. So given an array in C star, I need to take some product, some composition of these birational maps composed with themselves. And by, if this is a negative number, then I mean the inverse of that automorphism. Okay. So, and then the wall crossing formula is that this clockwise product of these automorphisms of the torus remains constant as the stability condition varies. Okay. So there are some problems with making this rigorous as I've written it, but let me first discuss an example and then let's go back to that. So this example is related to the A2 quiver. So this is what happens when you study the DT theory of representations of the A2 quiver. So in that case, the Grothendieck group or the charge lattice is a two-dimensional lattice. It has two generators like this. And there is the Euler form, if you like, this skew-symmetric form has, it's specified if I tell you that. And then basically there are two types of stability conditions, or I guess this is indeed a theory of class S, and the Coulomb branch sort of has two chambers, which presumably correspond to weak coupling and strong coupling. But anyway, let me stick to the maths that I know. So there is a space of stability conditions. It is split into two parts by a wall, this blue wall. And on one side, in one chamber, there are only two stable objects, essentially. And on the other side of the wall, there are three stable objects. And so this is what the BPS invariants look like. On one side, there are just two non-zero invariants, and on the other, there are three. What I've said is not quite correct, because also that if you put a minus sign here, those would also, these BPS invariants, omega of gamma is the same as omega of minus gamma. But anyway, in the kind of positive chamber, there are two here and three on the other side. And then the wall crossing formula in this simple case tells me that the composition of those two birational maps I wrote there, corresponding to these two rays, is equal to the composition of three birational maps on the other side, which is corresponding to these three rays. Okay, so this dashed line means that, there is an object of this class still. I mean, there is an indecomposable object, but it's not stable. So, and the corresponding BPS invariant is 0. So in other words, these BPS invariants depend on your stability condition, but they depend on a kind of locally constant way. In one chamber, the DT invariants are constantly equal to this, and in the other chamber, they're constantly equal to that. But there is a wall dividing these two chambers, some codimension 1 wall in the space of stability conditions, and as you cross it, the BPS invariants suddenly change. Okay, and this is controlled by this, this wall crossing formula. And in general, there will be many more rays. There will be countably many rays. Okay, and there could also be infinitely many classes gamma living on a single ray with non-zero BPS invariants. So making sense of this, and to a certain extent this, is non-trivial. Okay. But in the context of the wall crossing formula, you can perfectly well do this. I mean, basically, instead of thinking about automorphisms of C star to the n, or what would be the same as automorphisms of Laurent polynomials, you basically think about automorphisms of a formal power series ring. And you can make sense of the wall crossing formula like that. But later, these sorts of issues absolutely are important, and they can't just be swept under the rug. However, for the sort of things I'm doing, even very simple examples like this one, this A2 example, are, the corresponding Riemann-Hilbert problems are hard to solve. And here there is no problem making sense of this formula. It really is just an equality of two birational maps of this torus. Okay, so then what's the Riemann-Hilbert problem? So I'm going to fix data as above. So in other words, I fix the stability condition, and then I have this data. And I also have to fix a constant term, which I'll explain in a second. So for now, it's just a map from gamma to C. And then the Riemann-Hilbert problem is asking for some piecewise holomorphic function from C star into this torus. Remember, this is just some C star to the n. And it has some, it's a function of t in C star. And there is some prescribed behavior as t goes to 0 or t goes to infinity. We'll come back to that in a second. But the key point is that as t crosses one of these rays, where there is a non-zero BPS invariant, it should jump discontinuously precisely by this automorphism of the torus. Okay, and by now you'll have realized this is not really an automorphism of the torus. It could be, in good cases, it's going to be a birational automorphism. But in general, it could be only defined on an analytic open subset. So making sense of this Riemann-Hilbert problem is a little bit of a tricky thing to do. I'm essentially sweeping technicalities under the carpet. Basically because I don't really take this too seriously, right? I mean, that you should consider this as an interesting suggestion and you should study it in examples and see what happens. I don't think it's reasonable to try and build a general theory on this as yet. So first we should study examples and see what's, find out what the answer looks like in those cases. Okay, let me just discuss a little bit here. So because we have a map from C star into the torus, there are also these characters of the torus. So if I compose with those characters, I just get maps into C star. So that's what I've done here. I've composed X with the character. And then this is saying that X gamma of T has kind of, well, exponential behavior controlled by the central charge. And also this constant term, which is where this theta is coming. That's as T goes to 0. And as T tends to infinity, of course, this K would have to depend on gamma. But basically there is some polynomial growth as T goes to infinity. Okay, and this is where we're strictly different to what Gauto, Moore, and Knightsky were doing. They had, at infinity, they had a condition like this, except Z was replaced with Z bar. Okay, so there was some kind of anti-holomorphic dual of the singularity at T equals 0 going on at T equals infinity. Okay, that's yeah. Okay, and so what about this constant term business? The way you should think about this is that really it makes more sense to think about a Riemann-Hilbert problem with values in a group, namely the group of some kind of automorphisms of this torus. But this is a very infinite dimensional group. And rather than doing that, I fix a point of the torus, which is really this e to the theta, and then I evaluate my map, I evaluate all automorphisms on that point e to the theta. Okay. Because that means that I can think about a problem which takes values in the torus, some nice finite dimensional space, rather than this infinite dimensional group. Okay, but that's morally why I'm having to choose this extra data of the constant term. It's just a kind of it's a fake to avoid thinking about this. And in practice, I mean, I've said holomorphic here, but in practice, when you study examples, you realize that you actually have to allow singularities in this thing at certain values of T. And that's, it's interesting to try and understand that. And also, I mean, this is this thing I was saying before. So when defining the wall crossing formula, you really can make everything rigorous. But to make this problem rigorous, at the very least, you're going to need some conditions on the growth rate of the omega gamma as sort of gamma gets larger and larger in the lattice. Because otherwise, these automorphisms, as I've defined them, are just not going to mean, they're not going to mean it. I mean, you need these to converge at least on some analytic open subset of the torus to make any sense of this formula here. Okay, so indeed, and I think physicists know or expect that if I were to do this in the context of coherent sheaves on a compact Calabi-Yau threefold, these omega gammas would grow too fast to make any sense of this as it stands. Okay, so, I mean, personally, I'm not so discouraged by that at the minute. I mean, I think we have to understand simpler examples first and then see what can be done in that very complicated context. And of course, on a compact Calabi-Yau threefold, we would have a hard time computing these invariants in the first place. So in a way, it's a rather academic question. Okay, so let me just see where we've got. So, just, I mean, there is some kind of, the most basic feature about DT invariants is that they satisfy this wall crossing formula. And the right way to view this wall crossing formula is that at each point in your space of stability conditions, there is some diagram like this in the complex numbers where you have a bunch of rays and attached to each ray is some automorphism of the torus. And then it becomes rather natural to think about a Riemann-Hilbert problem which has those taking values in the torus which has those jumps as you cross the rays. Okay, and so that's what we're going to think about. So what do we know about solutions to these things? Let me just show you show you some of these things. So the simplest case you can think about really is what you could think about really as the Donaldson-Thomas theory of the A1 quiver. So the quiver with just a single blob and no arrows at all. You have to sort of double it. So anyway, the result is that you take a two-dimensional lattice, and physicists would label these as electric and magnetic charges. Here's the pairing. You take some central charges for these things. So, you know, you have to specify the central charge of gamma E and gamma N. And the only BPS invariants are plus or minus gamma E. These are 1, and all the other BPS invariants are 0. And so the diagram in this case looks like this. There are just two rays where there is some automorphism, you know, where there is some non-trivial automorphism. So these are the rays corresponding to this ZE. And so we're going to get a function which is holomorphic on the upper half, you know, on this bit, and holomorphic on the lower bit, and with some discontinuous jump across this line. Okay. And I'm going to take the constant term for simplicity. I'm just going to take this to be 0. And so what is the jumping across this line? Well, it's given basically by this. Yeah, I mean, the thing that's causing the jump is gamma E. So the jump is controlled by the pairing with gamma E. So gamma E comma gamma E is 0. So this guy doesn't jump at all, and the other one jumps by 1 plus XE. Okay, so the fact that this one doesn't jump at all tells you you might as well, well, the solution is that it's just equal to its asymptotics. So it's very easy to see that that's the solution of the Riemann-Hilbert problem as far as the character gamma E goes. But the character for gamma M is something more interesting. And as I say, there are kind of plus or minus. There are two parts to this function, one in the blue dots region and one in the orange dots region. And they have this exponential factor in the front. And then what's left is basically the gamma function. Well, it's really the modified gamma function. So this is the thing that you get if you take the gamma function, look at the Stirling expansion, and then take those first few sporadic terms in the Stirling expansion and exponentiate them and modify your gamma function like that. Okay, so, and, you know, well, it's a fairly easy exercise to check that this solution does what I claim it does. And it's a unique, you can show that it's unique. I mean, this is the only solution to that Riemann-Hilbert problem. Yeah. So one sort of nice thing you can do is you can actually superimpose such solutions like this and solve more general, you know, solve the Riemann-Hilbert problem for more general BPS structures, but only ones that are what I would call uncoupled, or I think Gauto more nicely called this mutually local corrections. It basically means that the automorphisms corresponding to different rays commute. Okay, so it's a sort of a Abelian problem. So if you're in the setting where you have only finitely many non-zero BPS invariants and you have this uncoupled situation, then you can solve your Riemann-Hilbert problem just by taking a product of solutions like this. So, you know, this solution jumps on this ray, now just times it by another solution which jumps on a different ray, and you will, you can solve your problem like that. Okay, so, and there is some way to encode this solution in this finite uncoupled case. It does not generalize to the coupled situation, but it's interesting because it makes contact with the topological string partition function. So I'm going to say that here. I should also say that the name tau function is a terrible one, which I apologize for. And I won't go into why I chose that name, but it would be better if it hadn't been called that. Okay, so let me just introduce some more notation where I take a basis for my lattice and I write the corresponding matrix for this intersection form. And then these functions, the central charges of these basis elements are actually local coordinates on the space of stability conditions. Now, this is something strictly different to what happens in the kind of physics situation. So, the central charges, let's think about a theory of class S, for example. The Coulomb branch is something like the Hitchin base. And these central charges are not local coordinates on that. Basically because the Hitchin base has half the dimension of this lattice, roughly speaking. But anyway, the space of stability conditions, this is really true. The functions, these zi's are always local coordinates. And again, I'm just going to be interested in the constant term theta equals 0. And I'm going to slightly, I'm going to get rid of the exponential term at the start of my solution. So let's assume that we can, well, okay, so I do this. And then this function tau is a way of encoding. You see, there is one solution here for each character. Or, I mean, you could just take them for the basis element, but still there are k solutions, if you like, k functions, k holomorphic functions, which are giving the solutions to the Riemann-Hilbert problem. And I can just encode them in one function like this. The fact that there is a function satisfying this identity is not clear, but it's true in this finite uncoupled case. I wouldn't expect it to be true in general, in fact. Okay, and in that finite uncoupled case, there is...
Tom, is epsilon jk the same as eta jk?
Yes, it is. Thank you. Thank you. Yes, it is. Yeah, so, I mean, one of the reasons I know that this formula holds in the finite uncoupled case is I can just compute what tau is. Of course, it's not very hard in really, I mean, we knew that this was basically the gamma function. We just differentiate the gamma function and then integrate it again. And the answer is that it's some kind of version of the Barnes G function. Again, modified by its leading order terms in its asymptotics, basically, as W goes to infinity. Okay, but this is quite a neat thing in that, you just plug in your BPS invariance into this formula. There's just one function, which you stick there, which you extracted from the A1 problem. And then if you want to solve the Riemann-Hilbert problem in the finite uncoupled case, you just write down this tau function like this and then differentiate, and that gives you the solution. Of course, these are extremely special cases, but anyway. Okay, so that's the solution in that case. And then there's some further results about this that I wanted to highlight, which is you can consider coherent sheaves on the resolved conifold. Okay, so a very simple example of a Calabi-Yau threefold, and think about coherent sheaves on that. We know all about the DT theory there. And that is actually an uncoupled situation because all the sheaves are supported on curves, and that intersection form is kind of the Euler form. Two curves on a threefold don't meet generically. So this is an uncoupled situation, but it's not finite because there are infinitely many BPS invariants corresponding basically to the different line bundles on the curve in the conifold, on the rational curve in the conifold. But nonetheless, you can solve this Riemann-Hilbert problem, and there is a solution involving certain special functions, and you can get your hands on this tau function. And it's interesting because on the one hand, it's some nice analytic function given by this contour integral. And on the other hand, it's asymptotic expansion as t goes to 0 reproduces the genus expansion in Gromov-Witten theory. So this is the, what are they called? I mean, this is counting curves that get contracted to points, and this is the rest. So, you know, you can think of this as a particular choice of analytic function whose asymptotic expansion, you know, is the string partition function. So in that sense, it's a non-perturbative topological string partition function. And you get at it by considering this Riemann-Hilbert problem. I should say what's going on with these. There's a bit being swept under the carpet. Basically, there's a few correction terms here and here. Somehow in genus 0 and 1, this isn't quite right. There's obviously something that we don't quite understand yet, but certainly, yes, you can read all about it in this paper. But yes, modulo a few small correction terms, this is the right answer. And the other thing is that some, so Kohei Iwaki and Omar Kidwai have been studying some very special examples of theories of class S which are uncoupled. So they basically correspond to kind of hypergeometric differential equations. So they are a very special class, but they showed that this above formula for the tau function, remember I just had a formula there which involved the BPS invariants, they showed that that coincided with the tau function that is computed by topological recursion. So in other words, the exponential of the free energy, where you have those FGs that topological recursion computes. I should say that, of course, in this context, there is always a quadratic differential knocking around. And you know, you take the spectral curve, which is defined by that quadratic differential. So that's another interesting link. Of course, we'd very much like to understand how to go beyond this uncoupled setting in this case. And maybe I'll just skip that. So, so here's the picture that goes with this. So you have the space of stability conditions. As I said, the coordinates on that are just the central charge coordinates, Zi. And then you should also think about the tangent bundle to the space of stability conditions. So the coordinates there are really Zi and these theta j. So you can think of that constant term. Remember I said that the constant term was an element of the torus, essentially, or really it was a kind of a logarithmic version of that. The element of the torus was the exponential of this constant term. The constant term was just a map from gamma to C. And you can think about that as a tangent vector to the space of stability conditions. So the input data for the Riemann-Hilbert problem can really be thought of as a point here in the tangent space to the space of stability conditions. You can then try and find your solution to the Riemann-Hilbert problem, and that will live, I mean, in theory, it lives in this torus T, but because there are all these birational maps gluing, you know, you should really think of it as living in a space which is glued by various copies of this torus. And in other words, it's something like the cluster variety. So this is the sort of geometry that one should keep in mind when studying this setup. And this solution, of course, depends on a parameter T in C star. Okay, so that's what I'm going to want to sort of move towards, is saying that thinking about this problem enables you to define a geometric structure on this space, the tangent bundle to the space of stability condition. Okay, so we'll see this picture again later. So I should speed up a little bit because I've only got 10 minutes left. So what about beyond the uncoupled case? So I just want to sort of briefly say this, see if it links to anything anyone knows. So in work with Davide Massoero, we solved the Riemann-Hilbert problem in the A2 case. So precisely that setting where I described the wall crossing formula. And I mean, really following ideas of Gauto, Moore, and Knightsky, the way to do this is to solve it geometrically using moduli spaces of connections on Riemann surfaces, essentially. So the actual details are a little bit different to what Gautam, Moore, and Knightsky did, of course. And in this case, the thing to do is consider a differential equation called the deformed cubic oscillator, which has already come up, well, is a very standard thing in the theory of Pain-Levé equations. So Pain-Levé 1 in this setting can be viewed as describing isomonodromic deformations of some deformed cubic oscillator. I'm just going to write down the formulae. They look kind of scary. I apologize for this. Oops, oops. So this is the deformed cubic oscillator. It's, you know, a second order ODE. The leading term, so, is just a cubic. But there are extra terms with coefficients h bar to the -2 and h bar to the -1. And h bar here is really this parameter t appearing in my Riemann-Hilbert problem. So if you set r equals 0 in this, this indeed exactly is what appears in the Pain-Levé literature. Yeah, probably goes back 100 years or something. And there is some small extra story. It's good to put this r in. But anyway, by studying the monodromy map for this differential equation, we were able to give a sort of complete description of the solution to the Riemann-Hilbert problem in the A2 case. And I should just say, what, yeah. So in terms of the coordinates we've been looking at before, the central charge coordinates are the integral of the square root of Q0. That's maybe what you would expect. And the theta i's are given by this thing. Okay, but yeah, okay. So that's that paper's on the archive, and yeah, so we can go beyond the uncoupled case, and there's obviously a lot more work to study more examples. Okay, so I have not so long left. So yeah, I sort of promised that there should be some geometry attached to these DT invariants. The key idea here is to think about this group of Poisson automorphisms of the torus. If we think about its Lie algebra for a moment, I mean, again, this is a sort of slightly heuristic discussion because, as we've discussed, the sort of automorphisms that are coming up are not actual automorphisms of C star to the n, they're birational automorphisms or worse. But let's anyway think about this Lie algebra for a minute. So its Lie algebra should be vector fields on the torus, preserving the this Poisson form. And you can see that you will, I mean, I guess I'm thinking about the case where this form eta is non-degenerate, so this is really a symplectic form. And then this has two parts, this Lie algebra. First, there are the kind of invariant vector fields, and those are given by this piece. And then there are Hamiltonian vector fields, which are basically given by functions on the torus, like this. So linear combinations of characters. And you should think of this decomposition as like a root decomposition, analogous to GLN being the diagonal matrices and the off-diagonal plus the off-diagonal matrices. And then the key insight really is that this wall crossing formula, this fact that the product of these automorphisms is constant, is analogous to an isomonodromy condition. If you've ever seen the theory of Stokes matrices and Stokes data, in the case where G is GLN, then that's the analogy we're making somehow. So what you should think about is some family of connections with values in this group. So you take trivial G bundles over P1, T is the parameter on P1, and Z and F are elements of this Lie algebra. Z is the central charge, and F is some function on T. And the point is, you don't really know what this function f is. You know the central charge, but you don't know what this function f is. But what you do know is the Stokes data of this connection, because that should be given by the dt invariants, or rather by these automorphisms defined by the dt invariants. So you can say that what you're trying to do is get at these functions f, which are somehow implicitly defined by the dt invariants, by the statement that this connection should have Stokes data given by these invariants. Anyway, that was the sort of way of thinking that I was pursuing. And it leads to an interesting output, which I guess once you have that output, you can throw away this picture, which is that you can study connections like this in the much simpler setting where G is GLN. Here you would put some diagonal matrix, and here you would put some off-diagonal matrix. And this is a standard part of, for example, de Brovin's theory of Frobenius manifolds. And if you want the Stokes data to be constant, which is really what this wall crossing formula is telling us, then this function f has to vary as a function of z, right? So in a very special way. And that is controlled by something called the Iso Monodrome equation. And in this setting, that comes down to this equation, okay? Now, basically, so if you use these, so each of these is a holomorphic function on the space of stability conditions. If you insert this extra factor here, this becomes a function on the total space of the tangent bundle. And this differential equation translates into this differential equation. And so, I followed this line of thought and wrote down this equation, and I thought that nobody would have ever thought about this before. But it turns out that this is, and Ian Strawn wrote to me to tell me that this is a well-known differential equation in the differential geometry community, and it's called Plebanski's second heavenly equation. And in fact, this line of reasoning that I've just been outlining goes back to Mason and Newman in the 1980s. The idea that if you take the Iso Monodrome equations for GLN connections and then put instead this Lie algebra of vector fields, then you end up with this second heavenly equation. That was something that they had also observed many years ago. So all this tells you that there should be some complex hyperkähler structure. So it's a standard thing. This is why Plebanski wrote down his equation. It describes hyperkähler metrics. And so you can just write down what this is now. So this is a complex hyperkähler structure. So it has I, J, and K, and a complex metric here. So this is the inverse to the matrix eta upper Ij. So I'm having to assume that's non-degenerate at this point. But basically, this hyperkähler structure is given in standard form in terms of these vector fields, Vi, which is the obvious thing, but Hi where this W enters. So this is some more complicated. And the more geometric way of saying all this is that the solutions to the Riemann-Hilbert problem are annihilated by this, so they're constant along the flows of this vector field here. So, I mean, this is explained in that paper. And there's been a recent paper of Sergei Alexandrov and Boris Pialin, which explains this. Well, I mean, it does many things actually, but one of the things it does is give physical interpretations to this function, for this function W, and also the tau function I was talking about before. So I'm very excited that some physicists have got involved in explaining what some of these things mean. Okay, so I'm out of time. So let me skip the last slide and let me just go back to that. Yeah, okay, so maybe I'll just show it here. So I was going to talk about the twistor space, but I don't have time. But let me just, this is the picture that we've already discussed once, but with just the extra label. So somehow, again, the geometry here is that you take the tangent bundle to the space of stability conditions. That, the points of that define the Riemann-Hilbert problem. And so the Riemann-Hilbert problem can be viewed, the solution to the Riemann-Hilbert problem can be viewed as a map from here to this space X, which is more or less the torus. And then the sort of constant lines for this map define these vectors hi plus vi over t. So if you know this map, then you can extract the hyperkähler structure because you can work out what these vectors hi are. Okay. But I don't have time to talk about it, but I think, you know, the next step really is to, now we realize that there's a complex hyperkähler structure knocking around, the right thing to do is think about the twistor space of that hyperkähler manifold. But I'm over time, so I'll stop. Thank you.
Thank you very much, Tom. We have time for a few questions. You can just unmute yourself and ask, or you can raise your hand and I'll call upon you. Davide?
Yes. Hi, Tom. I'm Davide from Lisbon. I would like you to ask whether you expect that the Riemann-Hilbert problem and the linear Riemann-Hilbert problem as a unique solution.
As a unique solution. So my view is that the Riemann-Hilbert problem is a approximation to what the right question is. And in particular, I think, you know, what the answer is, can I draw one more picture? I think the twistor space of this complex hyperkähler manifold is what one should be thinking about. And the Riemann-Hilbert problem is trying to describe the twistor lines of this hyperkähler, of this twistor space. So the twistor space fibers over P1, and this T parameter we've been using is a parameter on P1. And what the Riemann-Hilbert problem is trying to do is describe twistor lines, describe sections of this map in terms of particular coordinates, these kind of cluster-like coordinates. So, you know, my feeling is that eventually we should throw away the Riemann-Hilbert problem completely. I think what we should be trying to do is construct this twistor space and think about its space of twistor lines. And, you know, if you have a solution to the Riemann-Hilbert problem, maybe you need to put some extra conditions so that it describes one of these twistor lines. So that's a very long answer to say that I don't really know whether there is a unique solution. Let me answer in a much more concrete way as well, which is that it's about what singularities you allow. So in general, we know that you cannot insist that your solution is holomorphic, because even in that A1 case, if you take non-zero constant term, then there is no holomorphic solution. So Anna Barbieri showed this. So, you know, it depends on which singularities you allow. And if you allow arbitrary singularities, then I think there will be far too many solutions. So, you know, it's a very good question about uniqueness. I think it's a difficult one. But it does certainly depend on what singularities you allow. Okay.
Are there further questions?
Can I ask a question?
Please, Boris.
Yeah, Boris speaking. My connection is pretty bad, so I hope you can hear me.
I can.
So, yeah, so you mentioned this remarkable coincidence between the tau function and the topological partition function for basically local Calabi-Yau's without compact devices. Do you have any idea what would be the replacement of the tau function if you go beyond this class? Because clearly the topological partition function is well defined on any toric Calabi-Yau and possibly any compact Calabi-Yau as well.
Yes, it's a great question. I mean, I could go for the simple answer of no, but so the thing I've been trying to think about is making connection with work of Jörg Teschner and his collaborators, where they study, where they relate partition functions to Painlevé tau functions. So because, you know, as we saw, the first coupled case where I can solve this Riemann-Hilbert problem is this A2 example. And already there you get a very clear link with Painlevé 1. And the Painlevé tau function is, you know, absolutely right in there. So I was trying to make contact with that work where Painlevé tau functions also arise. I mean, I wrote something on this last slide, so let me just say this, which is that, again, I think the key thing is the geometry of this twistor space. And there are these correspondences around where you take, if you take 2 points down here and look for twistor lines which pass through, if you take 2 points in the fibers over 2 points down here, then generically there will be a unique twistor line passing through those 2 points, and then it will hit a third fiber at a unique point. So thinking about twistor lines gives you these correspondences. And I imagine that computing the generating functions of these, I mean, each of these spaces is a kind of symplectic space. So you can describe these, you know, fix a point here, then you have a map from this fiber to that fiber, and you can try and describe that using a generating function. And I think those are I mean, that's what I really dream of, that somehow the partition function ends up being, having some kind of geometric interpretation as a generating function for some map, which is related to the geometry of this system. But for now, I don't have anything, unfortunately, completely concrete to say on that.
But do you expect that this correspondence would reduce to the tau function that you define in the uncoupled case? It doesn't sound obviously related, but
well, you see, what's the tau function doing in the uncoupled case? You're saying, first you're setting, for me, I'm setting theta equals 0. So that's really, I mean, if you imagine one of these points as being the origin and one of these points as being infinitesimally close to the origin. So this one, I mean, basically setting theta equals 0 is prescribing the tangent behavior of this twistor line. And then the tau function is somehow relating the solution, which I think of as its intersection with t equals 1, with its origin, which is the t equals 0. Sorry, I'm not explaining this very well, but I mean, the simple answer is I don't know how to make this work yet, but that's my hope, that there is some way to see this using the geometry of the twistor space.
Okay, thanks. That'd be very good.
Are there further questions? Let me try a really quick one.
Sure.
You've mentioned the theories of class S a number of times, but mostly on A1. Have you tried the general case?
Yeah, that's a good question. So, you know, I mean, theories of class S are this beautiful class of examples where, well, certainly mathematically, we know a lot about what's going on for A1. So let me say this. So what's the answer to this question? Basically, it gets very complicated when you go beyond A1. So in the A1 case, we know, for example, that the space of stability conditions is the space of quadratic differentials, and that the BPS invariants count finite length trajectories of those differentials. When you go beyond A1, physicists understand that what we should be thinking about is, well, I mean, first you should be thinking about elements of the Hitchin base, you know, for other groups, of course, which are already more complicated. But then it's really the trajectory structure that becomes very difficult to understand. And physicists, you know that what we should be thinking about is this thing called spectral networks. And, you know, they have very precise results computing BPS spectra by thinking about spectral networks. But spectral networks are really much more complicated than trajectories of quadratic differentials. I mean,
there's a fairly recent paper by Ionita and Morrissey. You might want to have a look at that. That's exactly what they do there.
Right. Yes. I mean, yeah, absolutely. I should do that. So, I mean, yeah, I mean, in principle, this extension could be made, but yeah, it seems. Yeah, maybe I'm just a bit intimidated by it, but we'll see.
Well, maybe we should call time. Mm-hmm. In fact, why don't we reconvene at 5 minutes past 1 to give people a little break, and we'll continue then. Thank you.